Okay, so we just talked about waves formed by a spring. Now let's talk about how waves form in water. And we'll first talk about the shape of the waves. That I'm sure you're familiar with water waves, but if you've noticed, there are basically two types of waves in water. They're basically circular waves, which you can see right here. Okay, and we have straight waves. Take a look at these. What you're seeing here are the troughs or crests, and therefore we actually have the wavelength right here. Similarly, you have the wavelength right here. Remember, the speed depends mainly on the medium, almost entirely. Okay, but in water, it will also depend on the depth, because when you change the depth, it actually will change the medium, the characteristics of the medium. So we'll get to that. So some key points. The principles of reflection, just like in collision theory, are the same. So if you have an object coming in, or an incident ray they call it, hitting this platform, it will bounce off. Here is its incident angle, and here's its reflected angle. It will bounce off at the same. So i.e. the incident angle is equal to the reflected angle. Okay, here these blue things are talking, these are waves, these are water waves. So if water waves are coming in, these would be straight water waves. You'd be looking at the crests here, or troughs. They come in, hit this, they'll bounce off in this manner. And this little line right here, this normal line, dotted, is actually invisible. So they'll come in like this, hit off. How we understand this is if you draw a normal down the middle. A normal, by the way, is perpendicular to the barrier. Okay, so a normal is perpendicular to the barrier. That's what that symbol means. So that allows you to take the angle to the normal. A couple other things. So first of all, that was point 1 and 2. When a wave strikes a barrier that's parallel to the wave source, it will be right back. So in other words, if it came in here, it will just bounce right back. This point 2 talks about what I just talked about with the normal. Point 3 says when a circular wave strikes a straight barrier, an arc is formed. What does that mean? Here is a circular wave. Strikes, this is a bent barrier, and straight waves are formed if a circular wave, going out in all directions, hits a straight barrier. You can imagine that this point is going to hit first. Therefore, here's the after picture, you would expect these points to hit after, so they'll reflect after, and what you'll be left with is a nice arc. These points were the ones that hit first, these points were the ones that hit later on. You should know these pictures. These are quite intuitive if you just kind of think about what points will hit the barrier first, what angle they reflect at. Here we have a straight line. This is point 4. This is an important one, so circle this one. Hitting a curved barrier, as you would expect, they'll conform to the curve. In other words, this point will hit first and bounce off first. This point right here will hit last and bounce off last. The result is a curve. However, since it is curved, it will converge at a focus, at a point. Once it hits this point, here's the key part. Because waves pass through each other, this will become to a focus and it will branch out once again. Okay, it doesn't cancel each other out, only for a brief moment, from the principle of superposition, which still applies here. So all the amplitudes are added and they cancel each other out, but then they pass through each other and go along their way. You can see this if you take perhaps like a petri dish, fill it with a little, half a centimeter of water, and pluck your finger in there. So this is the dish. Pluck your finger in there and you'll see water waves form. Next thing you got to do is put some kind of a barrier. The petri dish, is actually circular. So if you send, perhaps with a pencil, start rolling your pencil in the water, and it'll send straight waves at this, but then you'll clearly see them reflect in this manner and then hit the focus and branch outward. This is important to understand. Now, wave refraction is when you have some kind of bending in a wave. So in other words, a wave is coming in, say it's a straight wave coming in, and then out of nowhere it starts to bend. Why will that happen? Happen for two reasons. It will happen if there's a boundary between two different media, so a shallow and a deep end, for instance. In this case, no bending. This is just the velocity will decrease because the media is changing, the medium is changing. In this case, in shallow water, it's going slower, and deep water, it's going much faster. And this is because the frequency slows down. And when the frequency slows down, the wavelength slows down, which means you're going to have a smaller velocity. Okay, I actually just completely lied to you. What I meant to say, sorry, is the wavelength decreases. I think I said the frequency. Whoa! What the heck? Sorry, I think I said the frequency decreases. That's not true. Frequency stays the same. Circle that. But the wavelength decreases. Frequency stays the same, wavelength decreases, therefore this must decrease as a number. You can see that here. Going to deep end to shallow end. Now, we actually can do some calculations with that. When you have two media, it's actually quite useful to be able to determine certain properties, what will happen, for instance, to a wave as it enters a different media. What will be its wavelength, what will be its future velocity. So for instance, in this example, the speed of the wavelength is 15 centimeters per second and 2.2 centimeters. If the velocity in shallow water is such, what is the wavelength? This is the formula. It's a simple ratio formula. Velocity 1 over velocity 2 is equal to wavelength 1 over wavelength 2. I'll do a question with you that's a bit trickier than that first one. So I'm assuming you've read through it. You simply will associate or allocate variables with the appropriate numbers given and solve for the missing variable. Here's the same thing. Waves travel, and this time it's a bit less explicit of what to do. Waves travel 0.75 times as fast in shallow water as they do in deep water. What will be the wavelength of the waves in deep water if their wavelength is 2 centimeters in shallow water? Okay, so first of all, let's do this. So here this will be shallow, this will be deep. Okay? Now it says waves travel 0.75 times as fast in shallow water as they do in deep water. So deep water, in other words, you can kind of allocate a variable for it. Okay, and I'm just going to leave it as v1 actually. Okay, or maybe it would just be easier to just erase this little equal sign. You'll see what I'm doing in a second here. What we know about v2 is that it's 0.75 times as fast as v1. It's asking for the wavelength of the waves in deep water will be if their wavelength is 2 centimeters in shallow water. This is actually solvable with the information I just wrote down, because while there's a 4-variable equation, I'm only given 2 values. I'm given a percentage of one of the other values. Watch what happens if I substitute this in. If I substitute this in for this, I have v1 over 0.75. v1 equals 2 centimeters over lambda 2. Check this out, a cancellation. Cancellation occurs, so you're left with 1 over 7.5, which is just some number, that's a 5. I used to be able to write. Then, we solve for lambda 2. That's a lambda, like I said. Writing used to be something I could do. Now, when you solve for this, kind of run out of room somehow, I'll be left with 2 centimeters times 0.75. So 75% of 2, which should be just 1.5. So, in other words, lambda 2 is equal to 1.5 centimeters. And that's that. So, some of the questions might be like this, might give you some indirect information about some of the variables that you have to be clever and allocate them accordingly. So really what we did here is that. Okay. And that is that. Now also what can happen is the waves can come in at an angle, and when they hit the media they'll actually bend. They'll bend because velocity is changing. In this case they're slowing down because it's going to shallow water. So these sides that hit first will slow down and kind of drag the front back, and in effect changing the direction. So you have foom going to foom like that. Okay, this is refraction. Refraction equals bending. Okay, now diffraction will be when we are bending along an edge. Okay, an edge or opening. Okay, what happens to waves as they move through an edge or opening? And as you'd expect, they'll adhere to, if it's water, they'll adhere to the edge, such that you'll have some kind of bend occur. So when these straight waves come in, they hit the barrier. These guys are allowed to pass through. These guys hit and they'll probably reflect. Okay, but what happens here is what's interesting. They'll come through, they'll adhere to this barrier, and the barrier will in effect attract the water, and the water will kind of suction to this, in effect bending the whole wave this way. There's a less bend here because it really depends on the wavelength, as I say here. If the wavelength is greater, you'll have greater bending. If it's shorter, you have less bending. And this is called diffraction. So here the diffraction is great diffraction. Okay, I'll put diffraction here. Greater bend, so greater diffraction. Less bend, less diffraction. You get the idea. You'll be expected to draw some of these. Same thing here. Here we have openings, really small opening. Okay, here I'm not sure what the heck happened here. There should be an opening here. Okay, openings here. Once again, wavelength comes in. Okay, less bend because in this case, as the size of the opening decreases, the amount of diffraction increases. Here, I guess I was trying to show that this size is really small, a small opening. The reason you have more of a diffraction here is because there are more collisions that is occurring. Think about it this way. If you have two holes like this, and you send a straight wave here, most of the wave will actually just pass through unperturbed. It'll just go right through. But some of it will hit this, in effect bending. So what you'll be left with is this. Not much bend, just on the outer edge. The closer these get together, the more bend you get. So the smaller the hole, the less, or the more bend you get. Remember that. Again, this rule that with wavelength still applies to this. So the greater the wavelength, the more bend you'll get as well. Talking about interference here, I have a nice little video that hopefully you watched that kind of explains it quite nicely, so I'm not going to get into that in this. If you have questions for that, send me an email. And let's do some of these practice problems, looking at some bending pictures. Okay, here, let's draw some pictures. Bending. Okay, try to keep the wavelength similar. You can draw some arrows to show it's bending. This is diffraction. Try to label it. What's this? It's around an edge, adheres to this, comes along, woo! Again, diffraction. Label it. Doesn't ask you to, but label it anyways. Here, this comes in. This is interesting. We take perpendicular, that's the normal. This guy comes in. Look at this angle. You can measure it if you want. I'm going to eyeball it to be right there. So in effect, this is basically coming out this way. The wave front will be like this. This is reflection. And our last example of this chapter, this is straight waves coming into a curved barrier. So you'd expect it to hit the barrier and be curved in response. Come to a focus, and then continue outward. Okay? there you have it. That is section 5.3. That is chapter 5, short chapter. Excuse me. Introducing you to the behavior of waves in different media, some simple calculations of waves, and a lot of theory and concepts.